Hello all, welcome to the final chapter. That's chapter 10. In this chapter we're going to move away from talking about ionic reactions and talk about a different reactive species. These are known as radicals. Let's take a look at the video breakdown. There will be 4 videos for this particular lecture. These include 1. The definition and formation of radical species, 2. A comparison of relative alkyl radical stabilities, 3. A discussion of the halogenation reactions of alkanes, and 4. A revisit of the anti-Markovnikov addition of hydrogen bromide or hydrogen chloride to an alkene. All of our discussions in organic chemistry so far have been confined to discussions about ionic reactions, and these typically involve the heterolytic cleavage of a sigma bond with the most electronegative atom taking both of those electrons in the bond. This has typically resulted in a positive carbocation species and an anionic species. Note that the positive charge represents a cation, whereas the negative charge represents the anion. So we've covered heterolytic cleavage, and so we're going to change tack and move to something that is not heterolytic cleavage. So there is a second way in which a sigma bond can be dissociated, in which both atoms take an equal share of the electrons, and this is known as homolytic cleavage and produces a species known as a radical. Radicals have an unpaired electron, and this is what makes them particularly reactive intermediates in organic chemistry reactions. Note that we use the double-headed arrow in heterolysis and we use a single-headed arrow in homolysis. There are 2 main types of radical species that you'll need to concern yourself with in this final chapter. Halogen atoms, when either irradiated with UV light or by heat, will produce 2 radicals. On this slide we see 2 bromine radicals from the dissociation of diatomic bromine. Note that the conditions used to produce these radicals are either UV radiation or heat. It isn't both. In the second reaction we see how an organic peroxide is cleaved by homolysis too. The R groups just simply represent alkyl chains. The action, whether it's by UV irradiation or by heat, yields a species known as an alkoxy radical. Again, please note that the use of a single-headed arrow, aka a curly fish hook, represents the movement of a single electron.
This concludes part A.
Hello, welcome back. This is video 2 of 4 for chapter 10.1, and in this video we're going to be discussing the relative alkyl radical stability. So alkyl radicals are formed by the homolytic cleavage of a carbon-hydrogen bond, and when this happens the unpaired electron is placed into a p orbital, and the carbon atom with that p orbital adopts a trigonal planar geometry. And this is the same as a carbocation. It therefore shouldn't come as a surprise that the relative alkyl radical stability parallels that of carbocation stability, whereby a methyl radical, though it's not showed on this slide, would be the least stable, and a tertiary alkyl radical is the most stable. This is also further supported by the bond dissociation enthalpies of carbon-hydrogen bonds. And by bond dissociation, this means the energy that's required to cleave that bond homolytically. So let's take a look at some of these now. The methyl radical has the highest bond dissociation enthalpy for a carbon-hydrogen bond. And this is to be expected, as the methyl radical, that's the intermediate that's produced from this, will be the least stable. However, note that there's not much of a difference between the carbon-hydrogen bond dissociation enthalpies between primary, secondary and tertiary carbon centers. Nonetheless, a tertiary carbon-hydrogen bond will yield the most stable radical, as it takes the least amount of energy to break that bond. Now, what do you think is the reason for the increased stability of the tertiary radical, and why does it have a lower bond dissociation enthalpy? Pause the video and resume when you have an answer. The video will advance to the next slide in 5 seconds, which contains the answer. The answer to this question is the same principle that provides the stability to alkyl carbocations of this series. That would be hyperconjugation. When a methyl radical is formed by the homolysis of a carbon-hydrogen bond, then the methyl radical is formed, and this slide shows that trigonal planar geometry and the p orbital of the carbon atom that contains the unpaired electron. Please note that these are neutral species and that the p orbital is perpendicular to the plane of those carbon-hydrogen bonds. For the methyl radical, there's nothing to stabilize the partially filled p orbital. The hydrogen atoms of the methyl radical are unable to donate any of their electron density towards that partially filled p orbital of that methyl radical. However, for the ethyl radical, which is a primary radical, it is now possible for one of the carbon-hydrogen bonds to donate its electron density, as shown, towards the partially filled p orbital. And as the number of carbon atoms increase around the carbon center, we can see this for the secondary propyl radical, the electron density now of 2 carbon-hydrogen bonds are being donated towards the carbon atom that contains the unpaired electron. Finally, the last radical has 3 carbon-hydrogen bonds which are able to donate their electron density towards that carbon that has the unpaired electron in the p orbital.
This concludes part B.
In this video, we are going to discuss the radical substitution reaction, aka halogenation reaction, and we're going to do this with methane first and then extend this to other alkanes. So the first thing that happens is a stage known as initiation, and it is in this stage that the halogen, that's chlorine, is dissociated through either the use of heat or UV light. And what happens is that as the chlorine dissociates, each atom takes one of the bonded electrons, and this produces 2 highly reactive chlorine atoms, aka radicals. Let's look at the next stage of the reaction. Radical substitution is a chain reaction, and this means that the product of one reaction is used to feed the next reaction, and that the second reaction provides a product which feeds the previous reaction. This stage collectively is known as propagation, and there are 2 key steps. In the first step, the hydrogen abstraction, a chlorine radical from the initiation step reacts with a molecule of methane. One of the carbon-hydrogen bonds has the electrons exposed on methane to show how that carbon-hydrogen bond breaks to form a methyl radical and how a bond is formed between hydrogen and the chlorine radical. This stage, as I said, that's the hydrogen abstraction stage. The methyl radical propagates, is carried through to the next step, which is the halogen abstraction. This highly reactive species undergoes halogen abstraction to form the main product, chloromethane. Bonds form when the 2 unpaired electrons move towards each other. The diatomic chlorine bond is broken homolytically during this process, and this forms a chlorine radical which feeds back into step 2. The third stage of this reaction answers the question of what happens when 2 radicals meet each other. Let's take a look at this now. This stage is known as termination. The coupling of any 2 radicals depletes the supply of reactive intermediates and terminates the chain reaction. Several pairings are possible, and these are shown here. More chloromethane can be made, or 2 methyl radicals can be combined to form ethane. Finally, chlorine atoms or radicals can be combined to form diatomic molecules of chlorine. Let's now take a look at the use of chlorine and compare this when other alkanes are subjected to halogenation. Higher alkanes react with halogens by the same kind of chain mechanism as those that we have just seen. Ethane, for example, reacts with chlorine to produce chloroethane. However, Alkanes that contain more than 2 carbon atoms will give a mixture of isomeric monochloro products as well as highly chlorinated products seen on the next slide. And the percentages given are based on the total amount of monochloro products seen in each of these reactions. The ratios of products that we obtain from chlorination reactions of higher alkanes are not identical to what we would expect if all of the hydrogen atoms were equally reactive. We find that there is a correlation between reactivity of different hydrogen atoms and the type of hydrogen atom, that's primary, secondary or tertiary, being replaced. The tertiary hydrogen atoms of an alkane are most reactive, secondary hydrogens are next reactive, and primary hydrogens are the least reactive. Now, we can account for the relative reactivities of the primary, secondary and tertiary hydrogen atoms in a chlorination reaction on the basis of homolytic bond dissociation energies. Of the 3 types, breaking a tertiary carbon-hydrogen bond requires the least energy, and breaking a primary carbon-hydrogen bond requires the most. Since the step in which the carbon-hydrogen bond is broken, i.e. the hydrogen atom abstraction step, determines the location or orientation of chlorination, we might expect that the activation energy for abstracting a tertiary hydrogen atom to be the least, and that the activation energy for abstracting a primary hydrogen atom to be the greatest. Thus, tertiary hydrogen atoms should be most reactive, secondary hydrogen atoms should be the next most reactive, and primary hydrogen atoms should be the least reactive. Now, the differences in the rates of which primary, secondary and tertiary hydrogen atoms are replaced by chlorine are not large, however. Chlorine simply does not discriminate among the different types of hydrogen atoms in a way that makes chlorination of higher alkanes a generally useful laboratory synthesis, which means then that we need something that is better and more selective. We'll talk about this in a couple of slides. One complicating factor of alkane halogenation is the multiple substitutions that almost always occur unless an excess of alkane is used, as discussed on the previous slide. In this reaction, we see that if you mix an equimolar ratio of methane and chlorine, both substances are gases at room temperature, and then either heat the mixture or irradiate it with light at the appropriate wavelength, a reaction begins to occur vigorously and ultimately produces the mixture that we see here. Now, in order to understand the formation of this mixture, we need to consider how the concentration of reactants and product changes as the reaction proceeds. So at the beginning, the only compounds that are present in the mixture are chlorine and methane, and the only reaction that can take place is one that produces chloromethane and hydrogen chloride. But as the reaction progresses, the concentration of chloromethane in the mixture now has increased, and so a second substitution reaction begins to occur. That is, chloromethane can react with chlorine to produce dichloromethane. The dichloromethane produced can then react to form trichloromethane, and trichloromethane, as it accumulates in the mixture, reacts with chlorine to produce tetrachloromethane. And each time a substitution of chlorine for hydrogen takes place, a molecule of HCl is produced. Now, this is not very useful at all. And the other type of halogen that we can use, and is more selective, is bromine. So let's have a look at this on the next slide now. Provided that we keep the concentration of 2-methylpropane high, this reduces the chance of polychlorination as seen on the previous slide. However, the focus of this slide is to highlight the selectivity of the bromine radical over the chlorine radical when there are different carbon-hydrogen bonds ripe for abstraction. So the chlorine radical is more reactive, as shown by the product distribution. The bond dissociation energy of the carbon-hydrogen for the 9 possible substitutions of a primary carbon-hydrogen bond in 2-methylpropane does not prevent chlorine from extracting these hydrogen atoms, thus producing more of the primary alkyl halide than the tertiary alkyl halide. This is in spite of the fact that the tertiary carbon-hydrogen bond is lower in energy for this substrate compared to the bond dissociation energy of the primary carbon-hydrogen bonds, which is higher. However, bromination of the same substrate, that's 2-methylpropane, occurs by the usual radical substitution reaction mechanism, but it's slower and it's more selective because a bromine atom is a less reactive hydrogen abstraction agent than a chlorine atom is. Remember, these products are formed as part of the propagation step. Therefore, bromine is able to behave more selectively and will not react with the carbon-hydrogen bonds that are more available. That's those 9 carbon-hydrogen bonds belonging to primary carbons versus the 1 carbon-hydrogen bond that is attached to a tertiary carbon. The bond dissociation energy for this carbon-hydrogen bond is lower, and bromine being less reactive will only be able to abstract those tertiary carbon-hydrogen bonds, thus making the reaction more selective. Therefore, we see a greater than 99% tertiary alkyl halide product and only a trace amount of primary alkyl halide product.
This concludes Part C.
Let's revisit the anti-Markovnikov addition of hydrogen bromide to an alkene in the presence of an organic peroxide and explore how this radical addition reaction produces the anti-Markovnikov product. As a reminder, there is no stereoselectivity for this reaction. Here is the mechanism of how this happens. Only a trace amount of peroxide is required in order to get this reaction started, although of course at least 1 molar equivalent of HBr is required to result in the full addition of HBr to the alkene. So in the first step, the addition of energy, either in the form of light or heat, leads to the homolytic fragmentation of the weak oxygen-oxygen bond of the peroxide, thus forming 2 new radicals. These are alkoxy radicals. So just to give you an idea of how weak these oxygen-oxygen bonds are, the carbon-hydrogen bond is about 100 kilocalories per mole. That's quite strong. But the oxygen-oxygen bond is only about 35 kilocalories per mole. Now, if you heat it, it's going to lead to the homolytic fragmentation of that bond, and it's going to give us those alkoxy radicals. So when we get those alkoxy radicals, these are then able to abstract a hydrogen from HBr, giving a bromine radical. And it's the bromine radical that is the species that adds to the alkene. Let's have a look at this step now. The bromine radical then goes on to add to the alkene. In a relatively flat alkene such as prop-1-ene, the addition of the radical will occur with equal probability from either face. So the question is, which atom of the double bond does the free radical attack? The bond could break in 2 ways after all. Well, the answer is that the attack of the bromine radical is going to be on the less substituted carbon, because this results in a radical being placed on the secondary carbon. If we did it the other way round, it would be on a primary carbon. Now, radicals are electron deficient species and are stabilized by those adjacent electron donors. So, as we said, the more stable radical intermediate is the secondary free radical, and so this is why addition occurs predominantly at that less substituted carbon, i.e. the carbon that's attached to the fewest number of other carbons. And this explains the anti-Markovnikov selectivity of the reaction, because then in the second step, once we have that secondary intermediate, then that is going to now react with hydrogen bromide, and it's going to do a hydrogen abstraction. So the bromines ended up on the less substituted side and the hydrogen on the more substituted side. The bromine radical that is then produced feeds back into the propagation step until it's consumed. So in other words, the bromine is known as a chain carrier. Let's have a look at the termination step for this particular reaction. When the concentration of hydrogen bromide and the alkene becomes low relative to the concentration of free radicals, then termination starts to occur. And this can occur for a variety of specific pathways, these aren't shown, involving the recombination of two radicals to generate a new bond. Please note that these are only minor products, and the main product is the anti-Markovnikov product seen on the previous slide. Let's take a moment now to compare this reaction with the ionic addition reaction of hydrogen bromide. Both reaction mechanisms, that's radical and ionic, give addition products, but the main difference here is the regioselectivity and the reactive species. So in a radical addition mechanism, the bromine, we know, is now added to the less substituted carbon of the double bond. And this leads to the formation of the more stable secondary radical intermediate. This will then go on to abstract a hydrogen from hydrogen bromide, and that will give us then the anti-Markovnikov addition product. The other mechanism that we've seen on this course results in a Markovnikov addition, and this is where hydrogen bromide adds to the carbon which is less substituted. And this places the positive charge, so this is an ionic reaction, onto the secondary position, and the bromide anion attacks here. Finally, there is a similarity between these two addition mechanisms, as they both result in the formation of syn and anti-products when there's the possibility of a chiral center.
This concludes Part D.